All right, let's do a simple kinematics problem. Let's start out by watching a little video clip. We're actually going to do, instead of doing the Mini Cooper clip, we're going to do another clip with a drag race. So you can go ahead and watch that clip, or at least watch part of it. We're going to watch it from about 1:40 to 4 minutes. And you can find it by clicking right about here. Go ahead and watch that. All right, so we see in this clip that we'll just look at the winning car, the Lamborghini. So the Lamborghini finished this in a time of 10.8 seconds, and that in that time that it got to a final velocity of 132.3 miles per hour. That's miles per hour. Now we'll want to go ahead and convert that into meters per second, so 1 hour over 3,600 seconds. And 1 mile is 1609 meters. And that is going to be 59.14 meters per second. By the way, if you're good at doing these unit conversions, Google's, and you don't need to practice doing them, Google's really great for doing unit conversions. You can just say 32.3 miles per hour equals question mark meters per second. It'll spit it out for you. And our distance is 1/4 mile. And converting that into meters, we get 402.3 meters. All right, so now we have a distance, a final velocity, and a time. Let's try to find the acceleration right now. We're going to come back to our kinematics equations. I'm going to start with this one. V is equal to V naught plus AT. V naught here is 0 because the car is initially at rest. And I want to solve for the acceleration. So my acceleration is V over T. That's my final velocity, which, what was it? 59.14 meters per second, divided by my time, which is 10.8 seconds. Now let's look at our units. We get meters per second, or meters per second squared, which is appropriate. And I get 5.48 meters per second squared. Now, this assumes that our acceleration is constant, because remember, that was assumed when we derived our equations. I'm going to write that up here. Assumes constant acceleration. And so that means that the average acceleration is equal to the instantaneous acceleration. All right, so that's our velocity. All right, that's our acceleration found in that way. Now, let's also try to find our, let's take this information. We have our acceleration, which is our acceleration, 5.48 meters per second squared. We have our time is 10.8 seconds. And now I want to know what is our x value. I'm doing this. I know that we already have the x. We know that it's 1/4 mile, but I want to illustrate something for you. So let's try to find our x. From our kinematics equations, I know that x is equal to x naught, which I don't usually write because that's usually 0. V naught t plus 1/2 AT squared. All right, V naught is 0, so x just works out to be 1/2 AT squared. And then taking these values for x, I find that this is 319.6. meters. Now notice that this distance, 319.6, is quite a bit smaller than the actual distance that the car drives. So what jives here? Well, we can think about this in terms of our acceleration, because we're assuming a constant acceleration, but the fact is that the car, it probably is not accelerating at the same rate all the time. So let's consider two different scenarios. Let's say that I have my velocity and my time here, And I know that this is my initial velocity. I have an initial velocity here, and then I also have a final velocity. And I know that that final velocity was given, it is 59.14. So we're up here, I have 59 meters per second. And down here, I have 0 meters per second. And I know that those 2 points are true because they're given. Now, I can go in several different ways. I can go this way to get there. All right. Or let's imagine that I can go like this, where I increase my velocity in a certain way, and then I increase in that way. Now here, the acceleration is bigger in the first part. So I'm accelerating at a faster rate in the first part. And then in the second part of the race, I accelerate at a slower rate. All right, so my acceleration is big initially. And I say that it's big because I have a big slope right here, and then I have a smaller slope. The other alternative is that I accelerate at a slower rate in the beginning, and then I speed up in the end. So which is it? Am I doing the green, where I accelerate quickly at the beginning and then slow down at the end? Or am I looking at the purple, where I accelerate slowly and then faster? Or is it somewhere in between, like the red? Now, the red would give me this distance. So accelerating at the rate of the red, I would go 319.6 meters. Now remember, V versus T graphs, the area under a V versus T graph gives the distance covered. All right, so 319.6 meters on this graph is that area. So which is it that I'm doing? Well, remember, we go actually a further distance, 402.3 meters. So then I can assume that my acceleration looks more like this. That is that I have a big acceleration initially, and then a smaller acceleration as I move faster and faster. And that seems to make sense, that as the car goes faster, it actually accelerates at a slower rate, because we'll get into this with energy, but as you go faster, it requires more energy to go faster. All right, so you begin to slow down in your acceleration. And that works out with the numbers as well, because I actually travel a further distance than I would at this, for this range, doing the 5.48 meters per second squared. All right, so that's a basic kinematics problem. Given some initial values, finding the acceleration or the distance or the velocity. And we'll stop there and we'll pick up with another one in just a moment.